I'd like to talk about Mills theory and Fermionic path integral. And Lars Brink, organizer, told me to cover at least some part of the Fermionic path integrals and anomalies. And it's a little bit old subject, but I found this very relevant to this conference because much of the works around this one was performed at the Professor Jan's Institute at Stony Brook around 1980. And then, if time allows, I'd like to briefly comment on that. This is what I am working on recently, namely bosonization in path integral. This is the application of the chiral anomalies, but how to understand it. And I found that some of the students are attending to this conference, and they told me to explain things the elementary way, but I'm not sure whether I'm successful in it. But I'm trying to be rather elementary. Mills theory, not only enormous success in real physics, but also they are stimulated many of the field theoretical machines, like path integral, for example. And many of my generation first encountered path integral when we studied Faddeev-Popov formula, for example. Therefore, I'll briefly explain what is the path integral, and what is the, for example, ghost structure, what is a ghost, and that kind of thing. Okay, so I just briefly first started. But in this gauge fixing, I use this parameter, and this parameter is, in fact, was first used by Professor Yang in the so-called Kushi limiting process. And but people nowadays often use this parameter to fix the gauge. And also, I mentioned we have a ghost and Grassmann. So I'm briefly explain it, and that's the Faddeev-Popov ghost antigo. And also, in the modern formulation, we often use the BRST. This is a kind of the supersymmetry. But again, Grassmann parameter appears in an essential way. So I just briefly start the what's the path integral. And there are many ways, but simplest way to understand is that to start with the so-called Schwinger's action principle. And this is a transition amplitude. Transition amplitude is essentially exponential of this Lagrangian. Therefore, if you take a derivative with a j, then this is a C number source function of Schwinger's source function. Then this one comes in front of the exponential, and that is one. Okay? So this is a Schwinger's action principle. And the solution of this is a path integral. That's a Feynman's path integral. And basic requirement of this path integral is that I'm going to briefly explain this property. Namely, epsilon is an arbitrary infinitesimal function, independent of phi. If it depends on phi, then you have to evaluate kind of Jacobian. But let me see. Independent of the phi, but infinitesimal arbitrary. This is a requirement. And to see to the, for example, just one page. You formally write this path integral, but this is equal to this, because just phi is replaced by phi plus epsilon everywhere. But we assume that this is equal to this. Therefore, this major part is the same. But we have some extra here. So if we expand this into powers of epsilon small, then you get the lowest order term, this one. Therefore, if you compare both sides, this part must be 0. That's the one. And this is the 0 means total derivative integrated is a 0. That is the equation motion in path integral. Okay. Always this structure, namely total derivative integrated, that is a 0. And if we use Schwinger's argument, this is related to the this is related to the operator relation. That's the equation of the motion. And by the way, this emphasis on equation modes are very similar to, again, Professor Yang's, Yang-Feltman formalism. And this formalism is often used in the non-commutative geometry, where canonical quantization is not quite clear, but still we assume equation motion, then use it. And in the same spirit, we can use this kind of path integral in the non-commutative thing, where canonical structure is not quite well defined, but we can later derive from path integral the canonical commutator. But so rather similar. But anyway, coming back to this basic requirement, at least we can think of two simple solutions. First one is that the ordinary complex field and formally integrate at all the points of the space-time. Then this is a usually integral, therefore translation invariant. And then another possibility is use Grassmann parameter. I will explain it briefly later. Then define, for example, left derivative. Because this left derivative, again, this property is more or less expected and in fact satisfied. And this gives rise to the bosons, this is like the fermions. And the Grassmann parameter is defined as anti-commuting everywhere. Therefore, psi x, psi y. In particular, if you take the equal space-time point, 0. So no magnitude. And this is the reason why Fermi particles are not defined as a classical wave. Electron is well known as a classical particle, but not wave until we discovered the quantum mechanics of field theory. Then I'm briefly come to the why we call the Faddeev-Popov ghost. And that's a spin statistical theorem. And in path integral, interesting how to understand it. And spin statistical theory means spin half integer the fermions, the integer the bosons. And there are three major conditions according to Pauli. Positive energy condition, causality, non-negative probability. And in the framework of path integral, this positive energy condition are rather subtle, but rather difficult to implement. So my proposal here is that to use Feynman's n-i epsilon as a positive energy condition. Because in the path integral, people often say this is a rather ad hoc way. But in my way, I emphasize that this is a more positive meaning. We are imposing positive energy condition. Because according to Feynman, due to this, positive energy particle propagate forward in time. Negative energy particle propagate backward in time. So always in any time slice, energy flow is positive. So we take it as a positive, and this can be implemented regardless of statistics universally. And this causality means anti-commuting or commuting at space-like separation. That can be also satisfied ordinary time ordered one. So only decisive factors are no negative probability. And therefore, positive normal condition decides statistics. And this can be done by analyzing the two-point function, namely propagator and residue of it. So in short, Dirac equation leads to Fermi statistics, and the Klein-Gordon type equation, including gauge field, leads to the Bose statistics. And because the Faddeev-Popov ghost follows the Klein-Gordon type equation, but nevertheless quantized fermion way, a Grassmann number. Therefore, that's a ghost. And this is independent of space-time dimensionality, dimension 2, 4, or any dimension. So now I come to the quantum anomaly. And this anomaly, the idea started around 1949. And for example, Steinberger is a good friend of Professor Yang. His paper is well known. But if you look at the reference 11 of Steinberger's paper, he mentions Fukuda and Miyamoto. And he says Professor Fujikawa, who was visiting at Princeton at that time, told Fukuda and Miyamoto paper to Steinberger. So he mentioned it. So historically, as far as I know, probably Fukuda and Miyamoto is the first. But anyway, around 49, Tomonaga, Schwinger wrote the papers related to this subject. And then, as is well known, about 20 years later, Berger, Keeb, and Adler wrote the famous paper. And the notion of anomaly was established around 1969. But also around the same time, Atiyah and Singer wrote the index theorem. And this is the fundamental properties of Yang-Mills theory related to topology. And because Atiyah and Singer are the mathematicians, young people often think that this is older than physics. But that's not the case in this case. Physics first appeared, and Atiyah Singer index theorem about 20 years later. But if you look at, for example, string theory, that's a bosonic string. This is a so-called Polyakov type string, but I learned that Lars Brink and John Schwartz, in fact, discussed it earlier. But anyway, if you do it, and if you do the Faddeev-Popov way, then you discover the Gauss number anomaly contains topological anomaly if you use the Gauss-Bonnet theorem. And this was later recognized as the Riemann-Roch theorem. This is a 19th century mathematics. And it is said that Atiyah and Singer was motivated by this theorem to generalize to higher dimensions. This is a two-dimensional theory, higher dimensions, and they, one of the motivations was this. So anomaly means a very interesting interplay between the physics and mathematics, and physicists are apparently earlier, but if you look at the Riemann-Roch, then mathematicians were earlier. So I now briefly explain how to understand the path integrals and anomaly. And so I consider the QCD type theory, and in particular Euclidean space, and that one. But in particular, I'm now specialized on the fermionic part, therefore this part. Okay. And the chiral transformation, although maybe students are not quite familiar, but anyway, chiral transformation is defined this way. In gamma 5, in the Dirac equation, we have the gamma 5, like chiral, new notion of the chirality appears Dirac equation, gamma 5. Then, because this is just a change of naming, therefore you see the identity. And this form of identity is a typical form. All the so-called Wall-Takahashi identities have this structure. Namely, you first write the path integral in terms of the original variable. You write the path integral new variable. But that's the change of the name. So must be identical. This is identity. So all the Ward identity or Ward-Takahashi identities are written in this form. And if you look at that only change of the action part, then you get the famous Noether's theorem, namely variation of action vanishes. So anomalous identity means you look at the change of measure part carefully, and here. And I'm going to explain that although there are some technical details, but at least Jacobian contains sufficient information to specify the anomaly. And then how to evaluate the Jacobian is a basic issue. So one way is formally define an exact fermionic path integral, very formal. Therefore, we first diagonalize the Dirac operator, and then write the this eigenvalue equation formally and normalize it, and expand the field variable in this complete set. And this is a Grassmann. Therefore, this coefficient are now Grassmann, and this is the ordinary function. Then we rewrite the path integral this way, and the path integral is well known to be the determinant, as Professor Faddeev explained yesterday. But this is we have the eigenvalue, And Grassmann means derivative. So if you perform integration, we get the product of eigenvalues. That's the definition of the determinant. So this is a very formal way about to define determinant in a more precise way. And our chiral transformation go in this way. So if you want to estimate the Jacobian, you have to operate in this basis, namely in terms of this eigenvalue space. Then you find that Jacobian is this way. And this is a very formal way, but this phi contains the information on the gauge field and how to extract it. And idea is that to replace this one by this. F is a regulator function, and F0 is unity. That means if you let the cutoff to infinity, this goes to 0. Then you come to original one. But you let this way. And by this way, you can now take summation to infinity. And so essential idea is that information of this one is now converted to this information of the eigenvalue, and then extract the anomaly. And that regulator function, there are several very simple, namely if F0 is unity means if you let cutoff infinity, no cutoff. And very large eigenvalue is regulated. So this is a condition. And this is some simple technicalities. But this is usually satisfied for any reasonable function like exponential minus x. Exponential minus x satisfies all this. That's a typical Hito kernel type regulator. Then we have this is the Jacobian factor. But this is the eigenvalue of this one. You can replace the operator. And so this is a well-defined operator, and some of it is, I said, we are taking trace. Trace of the well-regulated operator can be written down in any basis. Essentially comes to the plane wave basis. Then all the information now appears here. And the result is this. And from here to here, it may take about 1-page calculation, but I'm going to repeat it. But anyway, you get this. And this result is independent of this choice of f. Whatever you take, you always get this result, as long as this is satisfied. And one of the justifications of this procedure is compare with the Atiyah-Singer index theorem. Namely, I start with this one, and this is a regulator function. But because gamma 5 and D slash Dirac operator are anti-commuting, because of it, this one belongs to the eigenvalue lambda n, then this gamma 5 belongs to the minus lambda n. So they are orthogonal, vanishing. Therefore, here, most of them are orthogonal. Only the vanishing eigenvalue survives. And for vanishing eigenvalue, you can also specify the gamma 5 eigenstate. Therefore, this is replaced by plus eigenvalue minus eigenvalue. And this is called the index. And the index theorem, Atiyah-Singer type index theorem means this relates to the Chern-Pontryagin index, namely topological properties of Yang-Mills field. So this is an anomaly one. And this coefficient precisely agrees with this one. Therefore, anomaly means local version of index theorem. Therefore, even without topology like Maxwell field, we can still define the anomaly. But in the case of Yang-Mills, that's a beautiful topological property. And therefore, chiral identity, this is a naive Noether's theorem. We have extra one. And of course, there are many applications of this one in the standard model. But I just mentioned, for example, strong CP breaking in the analysis of the QCD, for example. If you change the Fermion field, then Jacobian gives this. But this is invariant, but this part is non-invariant. Therefore, if you modify the mass term, you also get the modification of the so-called theta parameter in the theta vacuum, like this kind of one. In particular, if you have no mass term, this can be free parameter, no strong CP violation, like that. Now I come to the Euler anomaly. Wild anomaly means wild transformation is defined this way. Namely, in the curved spacetime, metric is just multiplied. Because of it, the length of the spacetime distance is modified, but local angle is not modified. This is wild symmetry. And in the QCD type theory in D equal 4, this is a vector-like theory. It is well known that there are no general coordinate transformation, so-called gravitational anomaly that Witten and Alvarez Gomez like that. There are no general coordinate anomaly. Therefore, the anomaly actually arises from the wild symmetry. Conformal anomaly is actually the wild symmetry from this point of view. And therefore, to use this kind of transformation, we write down the Lagrangian action in a very formal way in the, this curved space. Then this one is the invariant under the wild transformation, like this. And the important, the fermion are the canonical 3 halves, and the Mills is a wild scalar. Well, I have to hurry. Then the important was how to define path integral measure. And then the path integral measure is a general coordinate invariant measure is written in this one. And one of the ways to understand is to look at this one. If you rewrite this one in terms of tilde variable, then all the metric goes away. So this is a number. But this part is general coordinate invariant. Therefore, this is general coordinate invariant. That's the idea. And important point is that when the wild transformation now becomes -1/2 instead of 3/2. And in the Yang-Mills case, again, we do a similar thing and first form the wild scalar and then same weight factor. Then this is ordinary scalar, but we have non-trivial factor, but any 1/2. Then we get the Jacobian factor and the same calculation as before, and we evaluate the wild anomaly. And this wild anomaly is known to be the lowest order beta function of the QCD type theory. And as I explained, in the case of Yang-Mills field, we go this way, and this factor gives the correct anomaly and asymptotic freedom to this one. So I just briefly mentioned the lattice one, and this is interesting, but time is running out, so I just mentioned the fact. Those people analyze the lattice one based on the Ginzburg-Wilson type one, and then they defined new gamma 5 on the lattice instead of simple gamma 5. Then we have the symmetry. And so this kind of the correspondence appears. And then you can, this is index-like analysis. And then you can derive the same way as the Jacobian factor. Then Jacobian comes this way. And if you take the very naive continuum limit, you come to the continuum theory. So this shows that the continuum result is a naturally derived, sufficient smooth gauge field. So this may suggest that, by the way, this kind of D was constructed by Neuberger. And this suggests that the chiral anomaly is a non-perturbative defined. At least suggests, and consistent with the Adler-Bardeen type theory. So brief summary so far is that I have explained that the path integral contains all the ingredients to understand the anomalies, at least. And as Henry Tai explained us yesterday, the anomaly in B and L in the standard model is very important to understand the baryon number asymmetry of the universe, or baryogenesis. And because of this anomaly, our picture of the baryogenesis changed completely, namely Sakharov type idea is no more used, and nowadays leptogenesis-like idea is common. So I just mentioned that David Gross mentioned the Dog and Schrödinger equation at the public lecture, but we might still be just like a dog. So when we understand one important aspect of quantum theory, then physics has changed. So deep understanding of quantum mechanics may lead to new understanding of beginning of the universe. Maybe we may, this is one example, but we may have the more new properties of quantum mechanics because we know how to use quantum mechanics, but we don't have we have not a complete understanding of quantum mechanics yet. That's my opinion. Therefore, we may still very much like a dong at this moment. And if you get a new understanding, then nothing like the discovery of new particles, but by this way, we may get a different way of understanding of the beginning of the universe, just like this baryogenesis. And this is a part of, the bosonization, and time is almost out, so I just briefly mention what is the idea. Idea is that this is a Schwinger's source term, and the fermionic path integral source is added. Therefore, we are considering the insertion of the vector particle, vector current. But in the two dimension, it is well known that this V can be written in this form. Then this is very much like the vector gauge field. You can transform away. This is actual vector. Then if you eliminate this one, you get Jacobian. And by this way, you can write this fermionic path integral in an equivalent way, bosonic one. And this current is replaced by the derivative of the scalar field. And so you have this kind of equality of correlation function. And what I tried recently that because this is a rather old idea, like Coleman and Roski and Sapsunik. But many people ask me how to understand this in path integral, because in CFT, people often use this. But in the path integral, we only discuss the current. So we just explained how to understand it. The idea is that to derive this kind of relation, the path integral, because this is on shell. If we go to on shell, then action vanishes. Therefore, path integral not well defined. But this is off shell, well defined. We can derive this one. And after this, if we go to the on shell limit, we go to this one. Anyway, this is the idea. And that's, again, bosonic one. This is the first quantization of the spinning string. We encounter the commuting fermions. But again, we can do the same thing. So anyway, in the two dimensions, the bosonization is a path integral. This is an old result. And if you add these two, then we can understand this kind of the way of bosonization rule. So conclusion of my talk is that Yamil theory and its quantization stimulates the development of path integral and related techniques, in addition to the remarkable success in describing various fundamental interactions. So this is a really remarkable achievement. But also we have the some of the development of technology. Thank you very much.
Let me make a short comment.
Yeah.
In case of Young-Mills and chiral fermions, there are two manifestations of anomaly. One is non-conservation of current, which you described.
Yeah.
And second is extension of Gauss law. And second cycle appears in the mutation relation of Gauss law. Both of these things can be described in terms of functioning.
Well, in this scheme, for example, if you start with the so-called BRST thing, then you found that the BRST current is no more conserved because of anomaly. Therefore, BRST constraint on the state vector is no more time-independent notion. Therefore, we can define. But you are aware of the more sophisticated commutator analysis, right? My way is a much simpler way, namely simply BRST current is no more constant, time-dependent notion.
Well, no, what I had in mind is that we can derive these anomalies for the Gauss law also in terms of functional integral.
Yeah. Gauss law is very
But
simple.
of course, everything is based on your Jacobian.
Yeah.
for
Okay.
Fermionic
Yeah.
fields, yeah.
Okay, I think we are running a little bit late.
Okay.
So let's
Okay. Thank you very much.
our end.